Hello, everyone. My name is Saeed, and I'm a PhD student at Georgia Tech. And in this part of the presentation, I just want to briefly talk little bit about the internals of the ASTRA-sim, what components it's made of, and what each component is exactly doing. Hopefully, that can give you a better sense of how ASTRA-sim internally is working and helps you if in the future you want to make some new changes to it, you can more easily find the components that you need to you need to change. And so I start with again uh, some category that Tushar also pointed to, that the different layers that points to the different layers of the assassin. And as you can see, and just it's a repetition of the previous talk, um, what we see is that if if we want to analyze the whole stack in the distributed training, what we observe is that the first two layers, this workload layer and system layer, there are not too many tools that cover this aspect in the simulation domain, while we have too many different network backends that are open source, and we can leverage those network backends for our usage. So the whole idea behind ASTRA-sim is that, okay, let's go and implement the workload layer and the system layer, and then integrate it with on top of any open source network simulator, and in order to model the distributed training platform overheads. Mostly, we are, as Tushar also mentioned, we are focusing on the communication overheads and its relation with a compute communication overlap. So the compute times are fed offline while we simulate the communications and capture the communication compute overlap in more details actually. So that's where ASTRA-sim sits in the simulation, and the kind of overheads that it models. So the workload layer, as Tushar said, it supports different parallelization strategies and like data model and hybrid kind of parallelization strategies. Then we have the system layer that you can think of it as a system software and communication library, like that tries to model the different collective communication and algorithms. Like it wants to mimic the behavior of like communication libraries that you may be familiar with, like Nickel, NVIDIA Nickel. It tries to model different topology-aware and hierarchical collective communication uh, um, algorithms, and also it supports different ways of pipelining this uh, communication operations to maximize the bandwidth utilization over your hybrid network. Then, on the network side, currently we support three different network backends. The analytical backend has its own variations. One variation supports congestion, and the other variation doesn't support congestion. Then we have the Garnet network, which is basically more suitable for modeling the on-chip and scale-up kind of like NVLink kind of networks. And then the new backend that we support is NS3. You may be more familiar with NS3, which basically can support any different data center topologies and data center networks, like NICs that are connected to the top of the rack switch, a spine switch. I have a slide that will discuss in more detail in the next set of slides. I will discuss it a little bit more. So the thing is, so this is the runtime structure of ASTRA-sim. Basically, what you do is that for each of these GPUs that you want to model, you create an instance of workload layer, an instance of system layer, and port it and integrate it with an instance of the network API. And each NPU has all these three instances, and then you are connected to the network simulator via this network API. So that's how you separate and put the boundary between the upper level system and workload layer with the network layer. And ASTRA-sim only talks, the only assumptions that ASTRA-sim has on the network side is it just assumes that the network simulator can support that network API. Then it doesn't matter what network simulator that you are using, ASTRA-sim is compatible with that as long as the network simulator supports that lightweight API, which is just a handful of abstractions that the network simulator needs to implement. So this is the general structure of ASTRA-sim. The source codes are in the ASTRA-sim file. Then then we have some example run scripts sit here. There's some sample inputs that are here. The network backends are within their own external repositories that can be cloned as submodules to ASTRA-sim. Then we have build scripts that are here, and the executables are also dumped or after the compilation are stored here. And we have some yes, and then we also have a workload generator which creates workload input files, the format for ASTRA-sim that I will describe at the end of this presentation. Okay, so let's talk a little bit about the internals of the workload layer in ASTRA-sim. So the workload layer currently supports two different interfaces. One is the text-based workload parser, and the new one that we recently added is this execution graph-based workload parser, which basically you can design the distributed training workload as a data flow graph, and that consists of several tasks, and then the dependency between these tasks are determined through the edges in that execution graph. And ASTRA-sim can basically parse that graph and simulate that execution graph-based training representation. And this is something that we will make it public in next few weeks. It's already implemented, and we are just doing some validation tests, and we'll release it very shortly. But in this presentation, I wanna talk a little bit about the text-based front end. So it's easy to define a new workload using this text-based front end, but the amount of flexibilities that you have is limited compared to the execution-based graph, which is very expressive. You can virtually simulate any types of parallelization strategy, very even irregular parallelization strategies, but it is harder to write execution graph workload input file. So depending on your usage, so most of the default parallelization strategies can be captured through the text-based front end. But if someone wants to really go and define any and write a workload file that is very customized, then you can use this execution graph parser. So the code structure of the workload file is inside the ASTRA-sim subfolder, and then inside the workload subfolder. So the main file for the workload is inside the workload.cp that it basically implements different training loops, data parallel, training loop, model parallel, and other types of training loops that we have are here. And one can easily add a new training loop here. The interface is pretty much straightforward. And in one example at the end of this that Taikyung is will present, you can see how you can change this training loop. So so in the high level view, the training loop is just a state machine which basically captures the compute communication operations and their sequence, their order in which we we execute these compute and communication operations. So complex relations can be captured through this simple, through decomposing that into simple estates that and then the order can be dictated by the edges in between these estates. So this is a very simple case of a data parallelization strategy, which basically here in this example you can see two NPUs that are doing data parallel distributed training, and each of those NPUs have this state machine as a part of their workload layer. So they start with the init state, then they just wait for so here we need to first make sure that from the previous training iteration, we don't have any pending communication for this layer. After we made sure, we just simulate the compute time for that layer that the GPU needs to perform and it needs to execute that layer forward pass. And as I said, computes are fed into the simulator externally via some real system measurements or other compute simulators. So what we do is modeling the communication and the relation between compute communication overhead in detail. So here, not too many fancy things we are doing here, because data parallel, we don't have any communication. We just iterate over these three states until we reach to the end of the forward pass. And in backpropagation, we now switch to a new state, which we basically want to account for weight gradient computation. So we need to perform some operations to calculate the weight gradients. Then what we do is just after that we issue. So in this case, we are doing layer-wise all reduce. So we issue the all reduce for that layer, and just after that we just go. It's a non-blocking communication because we don't need to. It's not. We don't need that for performing the input gradient of that layer. So after issuing that communication, we just go to a state that we basically want to account for the input gradient computation. And after that, we just go to the previous layer. So similar actions are happening here. We just iterate over these two states and issue all reduce after performing the weight gradient computation, and just go back to the previous layer. So after all of these, after we reach to layer 0, then we are good to go and start a new training iteration. And here, after we reach the init state, then for the layer 0, then we just iterate over these three states. And we want to make sure that now the communications are, if there is a pending communication for that layer, then we need to have a blocking wait for that layer because we cannot proceed. So the conclusion is that because of the data parallel strategy, you can issue the non-blocking communication and only have a blocking wait for those communications in the forward pass of the next training iteration. So this is what this training loop and this state machine is trying to implement. So what is the format of a text-based workload input file? So it's very, I mean, it's very straightforward, and that's why it's easy to define a new workload input file using this format. And here, so basically, we have implemented different training loops in the workload layer, and the first line just tells the ASTRA-sim what training loop should execute this workload file. And then we have some metadata that is workload specific. Then we have the number of layers that we have for this workload file, and then each layer basically captures the static behavior of the static behavior of each layer. So basically, the name of the layer, the time that it takes for the forward pass and the forward pass communication type, if that layer has some communication types or forward pass, then and then the size of that communication. Then we have the similar features for the input gradients, and then similar feature for the weight gradients. And then we have some parameter update latency, meaning that if this layer needs to update some parameter after the communication is finished, how much latency should we account, which is generally negligible. So, but here we add that latency if someone really wants to also account for that, those latencies after the communication is finished. And similar thing happens for the next layers in the next lines. So yes, so this is as I said, this basically tells the ASTRA-sim what type of compute communication operation this layer has, and what should be the order of these compute communication operations is dictated by the training loop that is a part of the workload layer. So training loop reads this information and then perform and then in a specific order executes these compute communication operations. And for more information, so we try to add more information about the execution graph based. So execution graph based frontend is a very powerful tool, and we have already implemented converters that someone can just clone and download a PyTorch model, compile it, and turns it into the PyTorch execution graph. And then from the PyTorch execution graph, we have implemented converters that convert that into the ASTRA-sim execution graph, and then directly run that workload on top of ASTRA-sim. So this is the vision that we have, is that in the future, any workload, the user can download any workload, compile it, and then run it on top of ASTRA-sim and simulate running that workload on a platform that doesn't exist. So one can easily see the effect of and the overall run end-to-end performance of this workload if it was running on this specific workload that is defined on ASTRA-sim simulator. Okay, so next I wanna briefly talk about the system layer of ASTRA-sim. As I said, you can think of it as a system software and communication library. So basically you have the system main file implemented here, and then you have the two major subdirectories of the collective and also the topologies, which basically is a logical topology. If you are familiar with collective communication, is that they create some logical topologies. It doesn't matter what underlying physical topology is, but if you are using, if you're executing ring-based or reduce, then ring-based all reduce assumes that you have a logical ring topology, and then runs all reduce on that logical ring. While in the physical topology, you might have a completely different physical topology. So this notion of logical topology versus physical topology enables you to run any collective communication algorithm on top of any physical topology. So this slide basically summarizes what I just said. So you have a logical topology, then the logical topologies are implemented in this directory. Then we have collective algorithms that are implemented in system collective. Sorry, this is a typo. And then collective algorithms can be implemented again. So each collective algorithm works with a specific logical topology, as I said. And then we have again, very similar to the workflow layer, we can express and define collective communications using a state machine. So what do I mean by that? So this is an example that Tushar just explained, and ring-based all reduced collective. And again, we can capture and implement this ring-based collective through a simple state machine. And the system layer, so these collectives are implemented in the system layer, and the system layer, you have some you have access to some send and receive primitives that the network API provides to you. So using those simple interfaces, you can implement complex collective communication algorithms. So here again, we start with init state. We just use that simple interface, send the data to our neighbor. So here we are assuming that this is a state machine implemented on NPU1. And here first we send to our right neighbor and then also receive from our left neighbor. And after that, we need to wait for the data to be received and then do local computation. And after the local computation, again, we just iterate here because it's a very simple ring-based algorithm. And you iterate over these 3 states until the reduced scatter phase is done. Then you iterate to this state where you are performing the all gather phases. And here, what you do is basically iterate over this one state. And in each iteration, you send data and send the data to your, basically broadcast the data to your right neighbor and just receive the data from your left neighbor. And once you receive the data, again, you send it to your right neighbor to broadcast the data that you just received to your right neighbor. So, and after that, after the last step, then you're done, basically. And using, again, this state machine, you can implement these kind of collective communication algorithms, and you can define and add new type of algorithms to the system layer if you want. And there is an abstraction for collective communication. All you need to do is just extend that abstract class and implement your own state machine, and then that will be a new collective communication algorithm. Okay, so now that you have the collective communications, the question is that how you wanna, if you have a hybrid network, how you want to utilize all of your network links at the same time. So to do this and to make it more realistic and close to real systems, if you look at the recent paper, for example, from Microsoft Collective Communication Library, what they do is very similar to what ASTRA-sim is modeling, is that they break it into chunks and then move these chunks across different dimensions of the network. So here, suppose we have a 3D torus. So ASTRA-sim internally creates 3 queues, each queue for each network dimension. And then when you have an all reduce, it can break it into multiple chunks. So this big all reduce is divided into 4 independent all reduces. And first we schedule on the first queue. The first queue is basically responsible for the first dimension of the network. So you start from the head of the queue, perform the reduce scatter of the first chunk, which basically adds and injects traffic to the dimension 1. And when it is done, then you do the reduce scatter of chunk 1 on the second queue. So now you are pipelining and overlapping the reduce scatter of chunk 2 on dimension 1 with reduce scatter of chunk 1 on dimension 2. So now 2 dimensions are engaged and are running in parallel. So after the warm-up is done, then now simultaneously all of the network links have some activity and each they have some chunks to perform the communication. This is a way to pipeline across different chunks and maximize the bandwidth utilization of the hybrid network that we have. So this continues, and we reach to a point where this chunk 1 is done. So we continue this process until all of these chunks are done, and after that we wake up the workload layer saying that okay, this was your communication and now it is done. Okay, so this is a high level overview that ASTRA-sim supports pipelining And if you define a hybrid topology, it tries to, and there are some tunable parameters of what should be the degree of parallelism. Everything can be configured by the user. And it tries, it captures this pipelining and parallel concurrency to maximize the network bandwidth utilization. So this is a system layer input file. Basically, it's just handful of parameters the user can set to tune the tune the algorithms and collective communication algorithms and the degree of concurrency for that specific experiment. So here, scheduling policy is LIFO. This means that if we have pending communications and a new communication arrives, we want to prioritize that new communication. And this is, and there are proposals in the research industry, in the research community that says that we should have a last in first out policy, because as we go backwards and we issue the new all reduces, those all reduces are more important for us because we need those all reduces to be finished sooner than the previous all reduces in the forward pass of the next training iteration. So that's why you can have LIFO versus FIFO kind of scheduling policies for collectives. This is just some constant delays to model some congestion and input overheads before sending a data out. For each send operation, we add this constant latency before sending that data out. And here, what we are doing is that we are basically saying that how many chunks per each network dimensions we want to run in parallel. So basically, that determines the degree of parallelism within a network dimension if we have a multi-dimensional network. Then this one says that if we are having an all reduce, how many chunks we want that all reduce to be divided in, or any type of collective. It's not just all reduce, it's just a parameter that says for any collective that is generated by the workload layer, how many chunks I want to split that collective into. So this is something for speeding up the simulation while sacrificing a little bit of the accuracy. And then here you define what type of algorithm you want to use for each collective communication pattern. So here, so basically ring means that for the all reduce means that because so this system input file is optimized for this 3D torus that I'm showing on right. Says that, okay, I want to break this all reduce into hierarchical all reduce algorithm. And because I have 3 dimensions, I want to use ring-based collective for each network dimension. So this is a natural way of doing all reduce on a 3D torus, because you have 3 dimensions and each dimension is also ring. So you want to perform ring-based collectives for each network dimension to because that's congestion-less pattern for ring-based physical topologies. And then similarly, you can define how you want to perform different other collectives like all gather, all to all, or reduce scatter. And this one is just one variation of how you want to perform all reduce, which you can find further details in the code base about that. So I don't want to go into too much details here. Okay, so this is as we can see, this is just the system where you can tune what type of algorithms and degree of parallelism you want when you are executing the communication patterns. And then in the bottom layer, we have the network layer that we port and clone as a submodule, and then integrate ASTRA-sim on top of that. And network backends are, as I said, are imported as submodules. So, and they will be cloned in this subdirectory in the external network backend. And then we have different network backends here. We have the analytical network backend, Garnet network backend, and NS3 network backend. And each network backend has its own input format, depending on what network backend is, and also simulates the network traffic in a specific with the specific details. So for example, ASTRA and Garnet are are cycle accurate simulators, while analytical is mainly using some sample equations to get the latencies. And here is where the network backend is integrated to ASTRA-sim. Basically, in the network backend, we have a main file that is the main file of the entire simulator. And then what you do is you create an instance of network API that is implemented by the network backend, and then you create an instance of system layer. And then once you are creating the instance of system, you pass these pointers to the system layer. So that's how these front-end and backend are integrated together, and the system layer internally creates its own workload layer. So all one needs to do is just create these pointers and then pass the network API pointer to the ASTRA-sim, and then this means these two, the front-end and backend, are integrated. And then once the integration is done, then you tell the workload layer to start injecting traffic and start simulating. And then you just inside your event queue, because all of these network backends are event-based simulators, you process all events, and because as you start the workload layer, it starts to inject events into the event queue of this network backend. And once all of these events are done, you just return. And here is for analytical backend and Garnet, you can find where this main file and integration is happening. And we release similar information for NS3 in the code base as well. So, okay, so this is just a comparison of Garnet versus analytical. And here you can see in the analytical backend, it supports hierarchical topologies, can be used for any network level because it's a rough estimation of the actual simulator, and it's appropriate for fast iteration over different configurations. And each level of the hierarchy that you can define can be switch, ring, or a fully connected dimension. And it, as I said, it uses simple equations to find the latency of each message that is crossing a link. So it's a very simple, but on the other hand, it's very fast. And it is accurate if you have communication patterns that are congestionless. So the example is that, for example, you are doing ring-based or reduce, and your physical topology is ring, so it doesn't create congestion if you are just executing one chunk at a time. So in that case, analytical backend can be accurate as well. And but it helps, and also at the same time, it helps you to get the overall latency very fast. While on the other hand, the Garnet, so the expressiveness, the type of topologies that it supports is like some switch-based and torus-based topologies. But the users can add new topologies to Garnet, but it takes a little bit of time in Garnet to add new topologies versus analytical backend. It's more appropriate for on-chip and or scale-up networks like NVLink. So because Garnet was originally developed for modeling the on-chip traffic. So if you are modeling distributed training, for example, on chip or between different chiplets, then Garnet could be a good network simulator for that network level. And it supports credit-based flow control, and it actually simulates the entire network protocol, like packetization, flow control, or congestion modeling. So it's much more accurate, and it's accurate in all scenarios. But the downside is that it's for large scale system, it is slow. And it's new NS3 backend that we recently integrated with ASTRA-sim in collaboration with UT Austin. It basically supports data center level networks, and it supports various data center topologies, and it supports RDMA, and more specifically RDMA over converging Ethernet RoCE network protocol. And also it models different congestion control schemes proposed for RoCE networks. And it's accurate in all scenarios, and you can now simulate the distributed training across the data center network, which is much more popular to study these days compared to, for example, on-chip or just a smaller scale on-chip distributed training platforms. Okay, so this is a rough comparison between different network backends. Depending on what your use case is, you can use any of these backends for your purpose. If you are more focused on-chip and chiplet-based, Garnet is the way to go. If you are more interested in data center networks, then NS3 is the way to go. And if you want to have a fast iteration over different configurations and for any network level, then you can use the analytical backend. And you just need to be careful that you tune the system layer in a way that creates congestion-less traffic. The recent analytical backend also have some rough congestion modeling scheme, which enables you to use analytical backend for congestion, for the communication patterns that create congestion. And we believe that based on our previous studies that you can reach to like 20% with 20% error, you can model distributed training for any network level while you have congestion. But on the other hand, it is very fast. So you can have a fast estimation of the end-to-end training with some error rate. Okay, so as I said, because we have different network backends, each network backend has its own format for input. And here I'm showing just different formats that you can see. More details can be found in their respective repository for each network backend. Okay, so now that we briefly described different levels of ASTRA-sim, let's look at a simple run script and see what should be done to just run ASTRA-sim. So basically, basically what you can see here is that you need to first find out, okay, where the binary, after the compilation, where is the binary file? What is the input file for the network layer? What is the input file for the system layer? And what is the input file for workload layer? And where do you want the stats to be dumped? After determining these directories, then you just call the binary, just pass these informations, network layer, system layer, and workload. And also, where do you want the stats to be stored after the run is finished? And just how many training iterations you want to simulate. And these are some stats. If you want to dump, if multiple processes want to dump to the same stat file, then also ASTRA-sim enables. And these are those flags to tell each process where in that shared folder it needs to run. So you can find more details on the code base regarding that. But roughly, you need to define the binary file and the input files for different levels, and then just pass it to the binary, and then it will start running and executing that configuration. So these are the runtime parameters, as I said, that you just pass it to the binary file. Okay, so now that I just briefly described how to run ASTRA-sim, let's look at what type of results ASTRA-sim is generating. So here, one file that you can see after run is finished is the end-to-end.csv, which basically tells you the layer-wise compute and communication and times, and also what percentage or how much of the communication time was exposed. Meaning that at some point the training loop had to wait for that communication. So the exposed communication is basically directly adds to the overall end-to-end training time. So this is the first layer of our DNN that we just simulated. Then this is just a run name for that we gave as a runtime parameter. And these are the compute times in terms of forward pass, weight gradient, and input gradient compute times. Then these are the communication times in microseconds. What were the raw communication time for each communication operation that this layer had. So this layer only had the weight gradient communication. So just you can see that's just the weight gradient communication is non-zero. And then how much of that communication was actually exposed? Here it turns out that the entire communication was exposed because it is the first layer. After this layer, we want to perform the forward pass, but we need to wait for the communication of this layer. So that's how that's why the entire communication is exposed. And then on the last columns of the first layer, you can also see the total compute and total exposed communication, meaning that basically how much time did for this experiment, what is the total compute time and what is the total exposed communication. So the summation of these two is basically the overall end-to-end training time. And you can find similar, and then we also have some detailed CSVs that I don't want to explain it too much. Just want to point out that you can find the queuing delays and average message latencies from the workload perspective when you are for each when you are performing the collectives. What is the average message latency you observed, and what was the queuing delay for each chunk for that collective communication. You can find, so these are very detailed information that if someone is interested, ASTRA-sim also reports these types of information for each layer of your DNA. So, so now here I just want to show some visualizations of the ASTRA-sim stats that can give you some intuition of okay, well, after I produce these stats, what kind of intuitions can those stats give me? So here is just a layer-wise raw communication latency for ResNet 50. And so here, one thing you can see is that different layers see different communication latencies. One thing you can see is these last layers see higher communication delays. One reason is that because here in this experiment, we are doing LIFO scheduling, we give higher priority to these layers. So that's why these layers needs to wait for a longer time. And that effect shows itself in the increased communication time for increased raw communication time for these layers, basically. While these layers usually, because it's a convolutional network, has less data to exchange and to do all reduce, but because of that queuing delay, you see that they waited and their communication took longer. And here you can see the layer-wise compute communication and compute and exposed communication, which basically tells you that the breakdown of the end-to-end training time and the factors which contribute to that latency. So here you can see that from those communication operations, only the layer 1 communication is exposed, and So the other communications are hidden behind compute. And this this is the exposed communication time. And the reason why it is very high is because at the time that this communication is issued, there are some running communication operations on the network that needs to be finished. So you see a lot of network traffic that doesn't let this communication to finish fast. So you have to wait for those, wait for the network bandwidth to be available for you because other communications are already in execution. And so this gives you the detailed overview. So this is a visualization of the detailed CSV that I just skipped and briefly explained. Basically tells you that for each layer, what are the contributing factors of different phases of the algorithm. So if you are doing hierarchical algorithm, you have multiple phases. And in each phase, you have a queuing delay, and also you have an average message latency delay. So you can see the breakdown of those delays and what is the contributing, what are the percentage that each of those latencies contribute when you are executing that collective communication pattern. And using ASTRA-sim basically enables you now to see and predict the trends for the future systems. For example, here it is showing that, okay, what happens if I just scale my number of NPUs and what are the percentage of exposed communication to total computation? As you can see, as you scale the number of NPUs, then your communication overhead becomes more and more, and then communication basically contributes more compared to the in the end-to-end distributed distributed training runtime. And this one basically shows, and also Tushar had a slide on that what happens if the scale of my distributed training platform is fixed, but now I'm enhancing the compute efficiency for each NPU. And then you can see that the share of, and then the value of the exposed communication increases because now you have less compute to hide the communication behind that. And although that the communication size didn't change, but the exposed communication time increased, the reason is that now there are more communications that are exposed and then show their effect on the end-to-end training time. So these are the type of trends that you can determine using ASTRA-sim. And so this concludes the different parts of the main parts of the ASTRA-sim. And here I just want to show also briefly describe some utility functions that we provide to ease working with ASTRA-sim. And one of these utility tools is workload generator, which basically you can define your workload in terms of the gem operations. So currently we are supporting gem operations, and then also define the partition strategy that you want. And then the workload generator automatically creates the workload input file for you, and then you can directly use that workload input file and feed and give it to ASTRA-sim. So here, for example, so this is the workload defined in terms of gem operations, and then this is the parallelization strategy that you want to have. So here is data parallel, and then this workload generator basically internally uses ASTRA-sim, which is another simulator that is developed by our lab that basically models the systolic array architectures like TPU, and uses ASTRA-sim to get the compute cycles for each of these gem operations. And also it internally calculates the communications operations and the communication sizes that you want, that it leads to for this gem operation and this parallelization strategy that you define. So then you don't need to get involved into directly define the work and directly write the workload input file for your for the new workload that you want to add. And the scale sim itself has its own parameters. Like if you want to use a scale sim, then you also can tune the systolic array architecture. So internally, you can also tune what type of accelerator that you are using to get the compute times. Okay, so here I just my presentation has ended, and in the next set of presentations after the break, my colleagues just show you how some hands-on exercise and some closing remarks on ASTRA-sim. Thank you very much for listening.